A classical bit holds a definitive 1 or a 0. A quantum state vector, however, relies on infinite probability amplitudes to map continuous superposition. To track a true quantum system, a computer must mathematically account for every possible state occurring simultaneously. Tracking this state vector requires exponentially multiplying memory. Adding a single qubit doubles the probability amplitudes, creating an immediate, intractable bottleneck. At approximately 50 qubits, the O of 2 to the n state space reaches a scale where no supercomputer on Earth possesses the physical memory required to house the continuous vector matrix. The simulation hits a strict mathematical wall. To solve the physical fragility that makes real-world qubits difficult to scale, physicists propose topological quantum computation, or TQC. TQC discards the fragile energy states of individual particles. Instead, it encodes quantum information into the global braided paths of hypothetical quasiparticles called non-abelian anyons. By physically swapping their positions, the overarching geometry protects the quantum state from local environmental noise. Synthesizing these physical anyons introduces a different barrier. Controlling topological excitations, such as Majorana zero modes in semiconductor nanowires, requires near-absolute zero temperatures and a level of microscopic precision that stretches the limits of current material science. Traditional topological computing effectively solves the quantum decoherence problem, but it requires trading an insurmountable mathematical limitation for an equally insurmountable physical engineering limitation. The UOR atlas establishes a structural alternative by abandoning the physical hardware entirely. Rather than attempting to trap subatomic particles in a dilution refrigerator, the framework maps exact topological logic onto a rigorous mathematical substrate. Physical anyons are translated directly into discrete data invariants. This schematic shows two paths from a genesis state. The left uses classical matrix expansion. The right uses UOR combinatorial braid evolution. Simulating down the left path tracks the expanding probability field, inevitably slamming into the intractable memory bound. Extracting a specific measurement from that expanded matrix requires a process called tensor contraction. That mathematical operation is computationally number P hard, effectively placing a strict ceiling on classical emulation. The combinatorial path executes a completely different mathematical protocol. By relying on discrete algebraic fusion instead of continuous floating point math, operations are evaluated as topological morphisms. The system processes the quantum logic without ever expanding the intermediate state vector. By mapping topological operations directly into discrete combinatorics, the atlas algorithmically bypasses the exponential memory barrier. For this discrete execution to accurately mirror continuous quantum mechanics, it requires a highly specific algebraic ecosystem. Classical physics tracks absolute spatial coordinates. Because topological quantum systems depend entirely on global, non-local properties, the atlas utilizes non-pointed S4 modal logic. This mathematically evaluates topological interiors and closures globally without relying on a physical space. Within this non-pointed logic structure, the framework establishes 24 invariant symmetry classes. These 24 classes form the finite combinatorial manifold for the entire system. Information navigates this space using exactly 3 topological generators: the fusion twist, the transposition, and the conjugation mirror. The fusion twist and transposition matrices strictly define how the non-abelian elements combine and exchange positions. They mathematically execute the braiding rules without physical subatomic particles crossing paths. The conjugation mirror acts upon the space by structurally inverting the data, satisfying the required algebraic symmetry of the model. Constraining all operations to these 3 topological generators successfully maps the continuous nature of quantum superposition into a strict, verifiable set of finite logical steps. A functioning topological computer must form a modular tensor category. The foundational requirement here is strict mathematical equivalence, meaning the evaluation of tensor products must yield identical topological invariants, regardless of the order of operations. This coherence is governed by the Mac-Lane coherence theorem, specifically relying on the pentagon identity for associativity and the hexagon identity for commutativity. The Yang-Baxter equation encodes this absolute. Swapping 3 adjacent threads starting from the left creates the exact same physical knot as starting from the right. The validation suite continuously asserts this against mathematical oracles. Every generated matrix operation programmatically obeys this structural equivalence. Discrete combinatorial systems face a critical mathematical threat. If the topological representation is completely finite, the simulated operations run the risk of collapsing into a restricted subgroup, destroying any ability to perform universal quantum computation. True computational universality requires fulfilling the Solovay-Kitaev mechanism. The available discrete operations must be able to densely approximate any continuous rotation within the special unitary group SU2. To prevent subgroup elapse, the atlas invokes the Friedmann-Larsen-Wang theorem. By calculating exact trace invariance restricted to the commutant subspace, the system empirically verifies a non-zero coefficient. This numerically guarantees that the traces are algebraically forbidden from falling into a finite exception. This rigorous structural proof confirms that the discrete representations act densely across the entire multi-qubit product space. The network achieves unqualified multi-qubit universal quantum computational power, mapped securely to a finite geometry. Moving from theoretical category theory into functional computer science brings us to the active software architecture, the UOR topological compiler. To execute classical quantum sequences like Shor's integer factorization or Grover's search, the compiler performs an algorithmic rollup. It dynamically maps standard quantum gates into robust topological instructions. The first stage of compilation breaks down continuous classical unitaries into the fundamental algebraic generators, the twists, transpositions, and mirrors. These decomposed elements are sequentially concatenated into a tightly bound operational string called a combinatorial braid word. Because the system utilizes S4 modal logic transitivity axioms, this concatenation operates natively on the topological invariance. The software calculates the algorithmic sequence without ever projecting the math into an intermediate state space. The underlying modular data driving these operations is structurally finite, restricting all permutations to the defined 24 invariant symmetry classes. Compiling complex quantum mechanics into topological sequences scales linearly. The entire preparation phase executes with high efficiency in classical polynomial time. This chart plots space and time complexity against algorithmic depth to illustrate the operational difference between continuous integration and discrete permutation. Standard classical quantum simulations track the full state vector. As algorithmic depth increases, the resource requirement shoots aggressively upward into O of 2 to the n territory, instantly overloading the system. The atlas evaluates those exact same quantum algorithms by combining combinatorial braids within a finite invariant space. The execution remains bounded, determining the topological outcome deterministically in O poly n time. By proving that universally dense quantum computation can be synthesized and verified on a discrete combinatorial manifold in O of n to the 6th time, the UOR atlas mathematically bypasses the continuous vector expansion. Under topological evaluation, this framework formally resolves the boundary between classical and quantum computing complexity, asserting that P equals BQP.